Hi everyone, I'm Janani and I'm going to talk about maximal independent sets in semi-streaming. This is joint work with Separ Asadi, Christian Conrad, and Kiran Naidu. I'm going to begin by defining an independent set. Any subset of vertices which don't have any edges between them is called an independent set. A maximal independent set is any independent set which is not a proper subset of another independent set. The example here is not maximal because we can add another vertex to it and get a larger independent set. The example now is actually a maximal independent set because the addition of any other vertex does not give an independent set. Finding the maximal independent set is usually easy in various models of computation just by following this framework. You pick any vertex, add it to the maximal independent set, remove the neighbors of this picked vertex, and recurse on the remaining graph. This simple process, in the end, always gives a maximal independent set. Why do we want to study this problem, MIS or maximal independent set? It is a fundamental problem in the classical setting, and it has a lot of connections to other interesting problems like maximal matching, vertex cover, coloring problems, and clustering problems. It has been used as a subroutine for other problems also, like correlation clustering. As a consequence, MIS has been studied in the local model dynamic graphs and massively parallel computation, including others. We're going to look at MIS in a semi-streaming model. Now I'm going to define the semi-streaming model. We have a graph G with n vertices and m edges, and the vertex set V is already given, and the edge set is not known. The edges are going to appear one by one in some arbitrary order, and this is termed as one pass over the edges. The issue is we don't have order of m space to store all of the edges, and we only have order of n polylog n space. This stream of edges may be repeated multiple times for multiple passes also. What do we know about MIS in the semi-streaming model? We know that if you have only one pass, it is not possible to find the MIS because you need omega of n square space. If we have log n passes, the randomized greedy algorithm given by Lou in 85 directly gives a semi-streaming algorithm also. But we can actually do exponentially better in semi-streaming. Ahn, Cormode, Guha, McGregor, and Worth in 2015, they gave an algorithm which only uses log n passes. This algorithm is actually the state of art for MIS in semi-streaming. The techniques used by ACGMW paper led to exponential improvements over the randomized greedy algorithm in other models also, like congested clique and massively parallel computation. So the natural question here is, can you do better than log n passes in semi-streaming? And now I'm going to talk about our result, which shows that you cannot do better, and any semi-streaming algorithm which finds an MIS needs omega of log n passes. And this is optimal because of ACGMW algorithm. Semi-streaming lower bounds are usually proven via communication complexity. Here, the edges are split between k players. These players can actually implement any semi-streaming algorithm because the player 1 can just run the algorithm on the edges given to them and send the memory state to player 2, who can then run the algorithm on the edges given to them, continuing from the state sent by player 1, and then send the memory state to player 3. This way, the algorithm can be run on the edges given to all the players for one pass, and at the end of one pass, player K can send the memory state back to player 1 for the next pass. So, any lower bound on the length of the messages communicated by these players to solve a particular problem gives space lower bounds for streaming algorithms also for the same problem. In the context of communication complexity, our result says that for any R at least 1, any R round R plus 1 party protocol for MIS requires n raised to 1 plus 1 over 2 raised to r minus 1 minus little o of 1 communication. And this is optimal up to n raised to little o of 1 factors. I'm going to talk about the one round lower bound of omega of n square, and then we'll see about extending it to multiple rounds. Here, the first part of the stream is going to contain two copies of a random bipartite graph. G1 and G2 are the same graph where each edge appears with probability half, and this is given to player 1. A special pair of vertices UV is chosen at random, and this is given to player 2 as the second part of the edges. Here, to choose this pair UV, we add auxiliary edges where every pair of vertices across the two copies are going to be connected except the copies of UV. That is, some W on the left, which is not U or V, is going to be connected to everything on the right, and the same thing is true for all the vertices on the right, which are not U or V. Any MIS in a graph constructed like this is going to reveal the existence of edge UV. This is because if, let's say, some vertex W was chosen to be in the MIS from the left, this means all the gray shaded portion on the right cannot be in the MIS and only U and V are left. So, if both U and V belong to the MIS, it means that the edge UV doesn't exist, and if only one of U or V is present, the edge UV exists. And this way, using the MIS, the existence of edge UV can be revealed. Again, if some W on the left is not chosen at all, and the only vertices in contention are U and V, the existence of edge UV is revealed in the first copy itself. So when player 1 sends a message to player 2, if this message is short of size only little of n square, since player 1 does not know what the special edge UV is, it cannot reveal much information about the existence of this edge. Since they don't know whether this edge exists, they don't know how to find the MIS either. And finding any MIS requires omega of n square space. Now, how do we extend this to multiple rounds? We're going to try to use a round elimination technique introduced by Miltersen, Nissan, Safra, and Vigdersen in 1995. Here, we start with a very good low communication R round protocol and get an R-1 round protocol out of this, which may not be as good, but it still has low enough communication, and continue this all the way till we get a 0 round protocol that does something non-trivial, giving a contradiction. And this will give a low bound on the communication used by the R round protocol also. How do we construct hard instances for round elimination for R rounds? We're going to start with K hard instances for R-1 rounds, and let's say solving each of these instances requires SR-1 bits in R-1 rounds. We're going to make one of these instances special with additional inputs, so that solving the R round instance requires solving I star. The players don't know what I star is at first, so in the first round, they don't reveal enough information about this instance. In the remaining rounds, they're going to have to solve I star without much help from the first round. So here, either the players send omega of k bits in the first round, where k is the number of R-1 round instances, which means this first round is going to help in solving I star, or they're going to send approximately SR-1 bits in the remaining R-1 rounds because they don't have any help from the first round. Now, how do we use this technique to get a low bound for 2 rounds? Let's say we replace multiple edges that we had in the 1 round hard instance with multiple 1 round hard instances themselves, and picking a special edge now is the same as picking a special 1 round hard instance. That is, we have multiple 1 round hard instances, and we have 2 different copies of these instances given to player 1. And player 2 is going to pick a special instance I star such that any MIS is going to find the MIS of I star also, just by connecting all vertex pairs across these two copies except the vertices in I star. There are two questions we need to answer here. If we want to get an n raised to 1 plus epsilon lower bound for 2 rounds, how many 1 round hard instances do we want? This cannot be too little because the first message cannot reveal too much about a randomly chosen instance. We need at least n raised to 1 plus epsilon instances so that only very small information is revealed about a random instance. The next question is how large do we want these instances to be? If they were too small, the players would just solve these instances in the next round. So we want at least n raised to 1 plus epsilon over 2 vertices in each of these instances to match the quadratic 1 round lower bound. The last thing we need is that these instances should be uncorrupted in a graph theoretic sense. That is, no pair of vertices can appear in two different instances because if they did, these players may collectively try to solve these instances together. We want these instances to be disjoint graph theoretically. We'll call this the inducedness property from now on. Let's do a basic vertex pair counting test here. The total number of instances we needed was at least n raised to 1 plus epsilon, and each instance was going to have at least n raised to 1 plus epsilon over 2 vertices. The total number of vertex pairs then from the inducedness property should be at least n raised to 2 plus 2 epsilon in an n vertex graph, which is not possible. So trying to directly implement round elimination did not work out. What we're going to do instead is solve multiple 1 round hard instances, each of them with a smaller size, to get a 2 round hard instance. And this is inspired by the approach of Conrad and Naidu from 24. The old round elimination had this framework. What we're going to do instead is take p times q hard instances for r minus 1 rounds, and solving each of these instances requires sr minus 1 bits in r minus 1 rounds. We're going to make one entire row of p instances special with additional inputs. We're going to make it so that solving the r round hard instance requires solving all of I1 star, I2 star till IP star. Here, we showed that either the players send omega of pq bits in the first round, which means they have some non-trivial advantage to solve the p special instances, or the players must send approximately p times sr minus 1 bits in the remaining r minus 1 rounds when they don't have any advantage. I'll briefly mention a couple of tools that went into proving this statement. The first one is direct sum arguments using information complexity. Here, we know that solving m independent copies of a problem is m times harder from the work of Barak, Braverman, Chen, and Rao. And the next one is message compression arguments. It was shown by Harsha, Jain, McAllister, and Radhakrishnan that if a protocol has high communication while having low information complexity, it is possible to simulate it with another protocol with communication roughly equal to the information used. Now I'll move from round elimination to graph instances. How do we handle multiple smaller instances? We have n over b times n over b subinstances, that is p equals n over b equals q. And each of these instances is on b vertices. We're going to pick a special t from n over b and make the entire row corresponding to t the instances that we want to solve. Now let's say each color corresponds to one particular group and we have two copies of 4 different groups of 2 instances each. If group green was the special group that we're going to pick, we're going to connect every pair of vertices across the 2 copies to each other, except for the vertices which belong to the green group. This is similar to how we constructed the 1 round hard instances. Now, we want each of the special instances in the green group to be induced. In addition, we don't want any edges shaded red to exist because these instances should not interfere with each other. Again, we'll call this the inducedness property. Let's see what we need to get a lower bound of n raised to 1 plus epsilon now. We want n over b square to be at least n raised to 1 plus epsilon because otherwise the first message will reveal too much information about our special row. We also need n over b times b square, which is the total communication needed to solve all the special instances in the remaining number of rounds to be at least n raised to 1 plus epsilon, so they don't solve the instances in the remaining rounds. And lastly, we'll need this inducedness property. How do we construct these graphs? We want n over b groups which form induced subgraphs of n over b vertex disjoint one round hard instances, and each of these instances is on b vertices. The basic vertex pair counting test that we did here actually passes through because we only need n over b square times b square vertex pairs, so only n square pairs. What parameters do we set here? If we want n over b square to be n raised to 1 plus epsilon and n times b to be n raised to 1 plus epsilon, if we pick b as n raised to 1 over 3, this actually gives a tight n raised to 4 over 3 bound also. Now we're going to look at how we construct these graphs. The inducedness property is very similar to this class of graphs known before and studied in the literature called Russo-Semeridi graphs. Here, to define these graphs, I'm going to define an induced matching first. A matching with no other edges between its endpoints is called an induced matching. So Russo-Semeridi graphs are graphs with approximately n groups, and each group is an induced matching of approximately size n. So this red highlighted edges form an induced matching, and so do these edges, and so do these edges. These RS graphs are locally sparse because they're just matchings, but globally they may be very dense because it is possible to pack a lot of matchings together. What we need instead is base graphs with n over b groups which form induced subgraphs of n over b vertex disjoint one round instances, and each of them is on b vertices. The RS graphs that we saw correspond to the case when b equals 2. We need to handle more intricate subgraphs instead of just plain edges on two vertices. We want these edges in the picture to be replaced by more intricate subgraphs corresponding to one round hard instances. We show that it is possible to construct these graphs where we have n over b raised to 1 minus little o of 1 groups of n over b raised to 1 minus little o of 1 vertex disjoint subgraphs, provided these subgraphs are n raised to little o of 1 colorable. And such graphs have appeared in the literature in the context of spanners and Hopf sets, but not, as far as we know, in the context of maximal independent sets or lower bounds for streaming algorithms. I'm going to give a brief overview of the construction. First, we construct a base graph on C layers, where C is the number of colors. Here, we can view this as stretching RS graphs, where we stretch the induced collection of edges or matchings into induced collection of paths. Here, each edge has been expanded into paths of length C. The first part of the construction is to create dense C-layered graphs on n over b vertices with approximately n over b groups of these induced collection of paths. In addition to being induced collections, we also want that each path here must be the unique shortest path between the start and end vertices. So the red edges between these two paths should not exist because they're induced, and the red path between the start and end vertices does not exist either. It is possible to construct these induced collections using average free sets. These are just sets where the average of any non-trivial subset of the elements is not present in the set. So if you have y1, y2, and y3, the average is not going to be in the set. It is possible to construct average free sets of large density. The next step in the construction is to replace each unique shortest path in this graph by the C colorable graph that we want to embed on B vertices, and we're going to keep one color class per layer. On the left, if we have the graphs that we want to embed inside this base graph, after embedding, we're going to get something that looks like this. Here, we won't have any corruption between these instances because any edge which crosses these instances can be traced back to a path in the original graph, and such paths do not exist by construction. Let's go back to the 2-round lower bound and give an overall picture. We're going to pick n raised to 2 over 3 times n raised to 2 over 3 hard 1-round instances on n raised to 1 over 3 vertices each and copy them twice and give them to the first player. We're going to pick a random group in each copy and connect all the vertices apart from the vertices in these random groups to each other. And we already showed that any MIS here is going to determine the MIS of all the special green instances. So this approach can be used to prove an omega of n raised to 4 over 3 communication lower bound for computing the MIS in 2 rounds. And it goes through for multiple rounds also to give our result. Here, to construct the R round hard instance, we used many groups of many R-1 round instances, and we used induced copies from our construction. And this gives our final result that for any R which is at least 1, any R round R plus 1 party protocol for MIS requires n raised to 1 plus 1 over 2 raised to R minus 1 minus little o of 1 communication. To conclude the talk, we showed that any semi-streaming algorithm for MIS requires omega of log n passes, and this matches the algorithm of ACGMW15. Many multipass semi-streaming lower bounds have been shown recently, but this seems to be the first time we can actually get optimal lower bounds in the number of passes. There are some open questions left here. What does this imply for MIS in the other models which are closely related to semi-streaming, like the massively parallel computation and congested clique? And can we extend the ideas presented here to other problems like matching and vertex cover in semi-streaming? Thank you for listening.